In our today's class, I will be taking first your doubts. So, doubt number 1 is question number 4 of exercise 5.1. Here, question is if a point C lies between 2 points A and B such that AC is equals to BC, then prove that AC is equals to half of AB. Now this you have to explain by drawing the figure. So solution is that first of all we'll write the given things given as AC is equals to BC and C lies in between A and B. As you can see in the figure I have drawn here. Now we have to prove that AC is equals to half of AB. As we know that AC is equals to BC, so name it as number 1 as it is given to us. Now we can add AC on both the sides of equation number 1, because as we know by our axiom that if equals are added to equals, the wholes are equal. So here we'll get our equation number 2, that is AC plus AC is equals to BC plus AC. Now LHS of equation number 2 will become as twice of AC and RHS of equation number 2 will become as AB. How? This also we can write from the one of the axiom, that is as things which coincide with one another are equal to one another. Now next is, if in this equation if we multiply both the sides by half, then we'll get AC is equals to half of AB. This is again by the axiom that things which are halves of the things are equal to one another. Now come to next doubt, that is question number 6. In this, if AC is equals to BD according to the figure, then we have to prove that AB equals to CD. Here again given is AC is equals to BD. Now we have to prove that AB equals to CD. From the given figure we will get that AC is equals to AB plus BC and name it as equation number 1. Now BD can be written as BC plus CD, name it as equation number 2. Now from equation number 1st and 2nd, what we can write? We can write it as AB plus BC is equals to BC plus CD. As AC is equals to BD is given to us, so from 1st and 2nd we can say by axiom that things which are equal to same things are equal to one another. Now subtract BC from equation number 3 on both the sides. So what you will get after subtracting? That AB equals to CD. Here also you can see that axiom is being applied, that is things which are subtracted from equals, then the remainders are equal. Now next is theorems or propositions are need to be proved. So we are doing our theorem number 5.1 first, that is two distinct lines cannot have more than one point in common. Now in proof what we'll take? We can take two lines L and M. You can see as I have drawn in the given question. Now we will prove that L and M have one point in common. So let us suppose that L and M have 2 points in common. We'll be doing it by contradiction method, so that's why I'm just supposing it oppositely, that is L and M have 2 points in common and name it as P and Q. But our assumption contradicts with the axiom that only one line can pass through two distinct points. So our assumption is wrong and we can say that L and M have 1 point in common. Now on basis of this theorem we will be solving some questions. So in exercise 5.1, question number 5 is, in question number 4, point C is called a midpoint of line segment AB. Prove that every line segment has one and only one midpoint. Let the given line AB is having two midpoints C and D. Okay, we are supposing that there are two midpoints C and D. So what we can write according to this, that AC is equals to half of AB, name it as equation number 1. AD equals to half of AB, name it as equation number 2. On subtracting first from second, we get that AD minus AC is equals to half of AB minus half of AB. So finally, according to the figure, we can write that CD is equals to 0, and this implies C and D coincide. Every line we can say that every line segment has one and only one midpoint. Come to question number 2. In this, we need to have an idea about the terms like point, line, ray, angle, etc. before defining the following terms. So, definition number 1 is, that is, part number 1 is parallel lines. Now, along these definitions, I have made figures also, so you can relate your this definition according to the figure. So, parallel lines, two lines L and M in a plane are said to be parallel if they have no common point, and we write it as L parallel to M. Second part is perpendicular lines. Two lines P and Q lying in the same plane are said to be perpendicular if they form a right angle, and we write them as P perpendicular to Q. Third point is line segment. A line segment is a part of line and having a definite length. It has two endpoints. It can be written as AB or BA. Then come to fourth point, that is radius of a circle. The distance from the center to a point on the circle is called the radius of circle. In the figure, P is acting as a center and PQ is the radius. Then come to fifth part, that is square. A quadrilateral in which all the four angles are right angles and all the four sides are equal are called a square. In the figure you can see that PQRS is a square. Then come to question number 3, that is consider two postulates given below. First is, given any two distinct points A and B, there exists a third point C which is in between A and B. Second is, there exist at least 3 points that are not on the same plane. Do these postulates contain any undefined terms? Are these postulates consistent? Do they follow from Euclid's postulates? Please explain. So in our solution we will be explaining this. So first is, yes, these postulates contain undefined terms such as point and line, because definition of point is that which has no part. Now here you can see that part is undefined, so point is also to be considered as undefined term. Similarly, the case is with line. Then next is, also these two postulates are consistent. Consistent here means where it is impossible to deduce from a statement that contradicts any another statement or proved statement. Now we can say that Euclid's 7 axioms are consistent, as 7 of them not contradicts each other. Here in this question also both the parts have two different situations, so we can say that they are consistent. Then first part is because as you can see that first says that given 2 points A and B, there is a point C lies on the line in between them, and second part says that C not lies on the line between them, on the line through A and B. So we can say that these two postulates are consistent. Then next is, no, these postulates do not follow from Euclid's postulates. However, they follow from the axiom, that is, given two distinct points, there is a unique line that passes through them. Then come to question number 7, that is, why is axiom number 5 in the list of Euclid's axioms considered a universal truth? So our solution, or you can say that it can be as statement is true in all the situations, hence it is a universal truth. Then come to example number 3. In this, consider the following statement: there exists a pair of straight lines that are everywhere equivalent from one another. Is this statement a direct consequence of Euclid's fifth postulate? Explain. So here you can see that first of all we will study about Playfair's axiom, that is equivalent to fifth postulate. So Playfair's axiom is, for every line L and for every point P not lying on L, there exists a unique line M passing through P and parallel to L. Now the distance of a point from a line is length of perpendicular from the point of the line. This distance will be the same for any point on M, L, and any point on M, L, and any point on L from M. So these two lines are equidistant from one another everywhere. You can see in the figure also. Now come to exercise 5.2 on the basis of these Playfair axiom and on the basis of above example, that is, how would you rewrite Euclid's fifth postulate so that it could be easier to understand? We can rewrite it as two distinct intersecting lines cannot be parallel to the same line. Come to question number 2, that is, does Euclid's fifth postulate imply the existence of parallel lines? Explain. Yes, if a straight line L falls on two lines M and N such that sum of interior angles on one side of L is two right angles, then by fifth postulate line M and N will not meet on this side of L. Also, we know that the sum of the interior angles on the other side of line L will be right angles too. Thus, we can say that they will not meet on another side also. You can see the figure of this question. Now you have to revise the in this chapter you have to revise the postulates and axioms. These are the main things, and on the basis of this only you will be able to solve your questions. So revise these postulates and axiom